Dear students, cordial welcome to massive open online courses in chemistry on Swayam. I am Dr. Amrita Anand. After going through this module, you would be able to differentiate between adsorption and absorption, to classify adsorption into physical and chemical adsorption, to explain the mechanism of adsorption, to explain the factors affecting physisorption and chemisorption, to explain the factors affecting adsorption of solute from solution on solids, to explain Free-Enriched adsorption isotherms. You would have noticed a number of people using masks to protect themselves from air pollution. Have you thought, how do these masks protect them from pollution? In this unit, we would take up the study of phenomenon behind such masks and many other applications of the phenomenon. We would be talking about the phenomenon of adsorption that occur at the surfaces or interfaces. This comes under the study of surface chemistry. The bulk phases that we come across in surface chemistry may be pure compounds or solutions. The immiscible phases are separated by interfaces. The interface represented by separating the phase is by a hyphen or a slash. For example, the interface between a solid and a gas may be represented by solid-gas or solid/gas. Due to complete miscibility, there is no interface between the gases. The interface is normally a few molecules thick, but its area depends upon the size of the particles of solid phase. Many important phenomena noticeable amongst those being corrosion, electrode processes, heterogeneous catalysis, dissolution and crystallization occur at interfaces. The subject of surface chemistry finds many applications in industry, analytical work and daily life situations. To accomplish surface studies meticulously, it becomes imperative to have a really clean surface. Under very high vacuum of the order of 10⁻⁻8 to 10⁻⁹ Pascal, it is now possible to obtain ultra clean surface of the metals. Solid materials with such clean surface need to be stored in vacuum, otherwise there will be covered by molecules of these major components of air, namely dioxygen and dinitrogen. In this module, you will be studying about an important area of surface chemistry, that is adsorption and its applications. Adsorption is essentially a surface phenomena. There are several examples which reveal that the surface of a solid has the tendency to attract and retain the molecules with which it comes into contact. These molecules remain only at the surface and do not go deeper into the bulk. The accumulation of molecular species at the surface rather than in the bulk of a solid or liquid is termed adsorption. The molecular species or substance which concentrate or accumulates at the surface is termed adsorbate, and the material on the surface of which the adsorption takes place is called adsorbent. The adsorbed molecular species can be removed from the surface of the adsorbent, and the process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption. These processes are clearly shown in the figure. Solids, particularly in finely divided state, have large surface area and therefore charcoal, silica gel, alumina gel, clay, colloids, metals in finely divided state, etc. act as good adsorbents. Let us discuss adsorption in action. If a gas like oxygen, hydrogen, carbon monoxide, chlorine, ammonia or sulfur dioxide is taken in a closed vessel containing powdered charcoal, it is observed that the pressure of the gas in the enclosed vessel decreases. The gas molecules concentrate at the surface of the charcoal, that is, gases are adsorbed at the surface. In a solution of an organic dye, say methylene blue, when animal charcoal is added and the solution is well shaken and filtered, it is observed that the filtrate turned colorless. The molecules of the dye accumulate at the surface of the charcoal. That is, they are adsorbed and the solution becomes colorless. Aqueous solution of raw sugar, when passed over beds of animal charcoal, becomes colorless as the coloring substances are adsorbed by the charcoal. The air becomes dry in presence of silica gel because the water molecules get adsorbed on the surface of the gel. It is clear from the above examples that solid surface can hold the gas or liquid molecules by virtue of adsorption. The mask used for the protection from pollution works on the principle of adsorption. It contains finely divided charcoal that adsorbs the pollutant gases and leaves pure air for breathing. Now, let us distinguish between adsorption and absorption. In adsorption, the substance is concentrated only at the surface and does not penetrate through the surface to the bulk of the solid, while in absorption, the substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in ink, the surface retains the color of the ink due to the adsorption of colored molecules, while the solvent of the ink goes deeper into the stick due to absorption. On breaking the chalk stick, it is found to be white from inside. Let X and Y be two different bulk phases in surface contact with each other. In absorption, if X absorbs Y, then Y would be uniformly distributed throughout X, whereas in adsorption, if X adsorbs Y, then Y would be found concentrated on the surface of X. In the other parts of X, away from its surface, the concentration of Y will be negligible. A distinction can be made between absorption and adsorption by taking an example of water vapor. Water vapors are absorbed by anhydrous calcium chloride, but adsorbed by silica gel. In other words, in adsorption, the concentration of adsorbate increase only at the surface of the adsorbent, while in absorption, the concentration is uniform throughout the bulk of the solid. This is depicted in the figure. Both adsorption and absorption can take place simultaneously also. The term sorption is used to describe both the processes. We now discuss the mechanism of adsorption. Adsorption arises due to the fact that the surface particles of the adsorbent are not in the same environment as the particles inside the bulk. As you see in the figure, inside the adsorbent, all the forces acting between the particles are mutually balanced, but on the surface the particles are not surrounded by atoms or molecules of their kind on all sides, and hence they possess unbalanced or residual attractive forces. The molecules at the surface have higher energy than those in the bulk. This extra energy per unit surface area is called surface energy. The residual attractive forces of the adsorbent are responsible for attracting the adsorbate particles on its surface. The extent of adsorption increases with the increase of surface area per unit mass of the adsorbent at a given temperature and pressure. Another important factor featuring adsorption is the enthalpy of adsorption. During adsorption, there is always a decrease in residual forces of the surface. That is, there is decrease in surface energy which appears as heat. Adsorption therefore is invariably an exothermic process. In other words, the enthalpy of adsorption delta H is always negative. When a gas is adsorbed, the freedom of movement of its molecules become restricted. This amounts to decrease in the entropy of the adsorbate molecules after adsorption. That is, delta S is also negative. Adsorption is thus accompanied by decrease in enthalpy as well as the entropy of the system. For a process to be spontaneous, the thermodynamic requirement is that at constant temperature and pressure, delta G must be negative. That is, there must be a decrease in Gibbs free energy. On the basis of the equation, delta G is equal to delta H minus T delta S. Delta G can be negative if delta H has sufficiently high negative value, as minus T delta S is positive. Thus, in an absorption process which is spontaneous, a combination of these two factors make delta J negative. As the adsorption proceeds, delta H becomes less and less negative. Ultimately, delta H becomes equal to T delta S, and therefore, delta J becomes 0. At this state, we say equilibrium is attained. There are two types of adsorption, physisorption and chemisorption. If accumulation of gas on the surface of a solid occurs due to weak van der Waals forces, the adsorption is termed as physical adsorption or physisorption. When the gas molecules or atoms are held to the solid surface by chemical bonds, then the adsorption is known as chemical adsorption or chemisorption. The chemical bonds may be covalent or ionic in nature. Chemisorption involves a high energy of activation, and therefore, it is often referred to as activated adsorption. Sometimes these two processes occur simultaneously, and it is not easy to ascertain the type of adsorption. A physical adsorption at low temperature may pass into the chemisorption as the temperature is increased. For example, dihydrogen is first adsorbed on nickel by van der Waals forces. Molecules of hydrogen then dissociate to form hydrogen atoms, which are held on the surface by chemisorption. We will now see some of the important characteristics of both types of adsorption. First, let us see the characteristics of physisorption. Number 1, lack of specificity. A given surface of an adsorbent does not show any preference for a particular gas, as the van der Waals forces are universal. Number 2, nature of adsorbate. The amount of gas adsorbed by a solid depends on the nature of the gas. In general, easily liquefiable gases have high critical temperatures and are readily adsorbed on a solid. This is because van der Waals forces are stronger near critical temperatures. For example, sulfur dioxide has a critical temperature of 630 Kelvin and methane has 190 Kelvin. Dihydrogen has 33 Kelvin. Thus, the amount of sulfur dioxide adsorbed by 1 gram of the activated charcoal is more than that of methane, which in turn is more than that of dihydrogen. Number 3, reversible nature. Physisorption of a gas on a solid is generally reversible. More of the gas gets adsorbed when the pressure increased because the volume of the gas decreases. So, the adsorbed gas can be removed by decreasing the pressure. This is according to Le Chatelier's principle. Similarly, we can describe the effect of temperature. Since the adsorption process is exothermic, the physical adsorption occurs readily at low temperature and decreases with increasing temperature. According to Le Chatelier principle, one of the variables if pressure, concentration or temperature that describes a system at equilibrium changes, then the system will shift in such a way that the change is nullified or minimized. Number 4, surface area of adsorbent. The extent of adsorption increases with the increase of surface area of the adsorbent. Thus, finely divided metals and porous substances having large surface area are good adsorbents. Number 5, enthalpy of adsorption. No doubt, physical adsorption is an exothermic process, but its enthalpy of adsorption is quite low, that is in the range 20 to 40 kilojoules per mole. This is because the attraction between gas molecules and solid surface is only due to weak van der Waals forces. Characteristics of chemisorption. Number 1. High specificity. Chemisorption is highly specific and it will only occur if there is some possibility of chemical bonding between adsorbent and adsorbate. For example, oxygen is adsorbed on metals by virtue of oxide formation and hydrogen is adsorbed by transition metals due to hydride formation. Number 3. Irreversibility. As chemisorption involves compound formation, it is usually irreversible in nature. Chemisorption is also an exothermic process, but the process is very slow at low temperature on account of high energy of activation. Like most chemical changes, chemisorption often increases with rise of temperature. Physisorption of a gas adsorbed at low temperature may change into chemisorption at a higher temperature. Usually, high pressure is also favorable for chemisorption. Number 3. Surface area. Like physical adsorption, chemisorption also increases with increase of surface area of the adsorbent. Number 4. Enthalpy of adsorption. Enthalpy of chemisorption is high, that is in the range of 80 to 240 kilojoules per mole, as it involves chemical bond formation. Number 5. State of adsorbent. Since a chemical reaction is involved, the state of adsorbate may be different in the bulk and on the surface of the adsorbent. Now, let us compare physisorption and chemisorption. Number 1. Physisorption arises because of van der Waals forces, whereas chemisorption is caused by chemical bond formation. Number 2. Physisorption is not specific in nature, while chemisorption is highly specific in nature. Number 3. Physisorption is reversible in nature, whereas chemisorption is irreversible in nature. Number 4. Physisorption depends upon the nature of gas. More liquefiable gases are adsorbed readily, whereas chemisorption, though depending upon the nature of the gas, gases which can react with the adsorbent show chemisorption. Number 5. For physisorption, enthalpy of adsorption is quite low, that is in the range of 20 to 40 kilojoules per mole. For chemisorption, enthalpy of adsorption is quite high, that is in the range of 80 to 240 kilojoules per mole. Number 6. Low temperature is favorable for physisorption. It decreases with increase of temperature. High temperature is favorable for chemisorption. It increases with the increase of temperature. Number 7. For physisorption, no appreciable activation energy is needed, but for chemisorption, high activation energy is sometimes needed. Number 8. Physisorption depends upon the surface area. It increases with an increase of surface area. Chemisorption also depends upon the surface area and it too increases with an increase of surface area. Number 9. Physisorption results into multi-molecular layers on adsorbent surface under high pressure, whereas chemisorption results into unimolecular layer. As mentioned above, the adsorption of a gas on a solid surface depends upon the pressure of the gas. The variation in the amount of the gas adsorbed by the adsorbent with pressure at a constant temperature can be expressed by means of a curve which is termed as adsorption isotherm. Freundlich gave an empirical relationship between the quantity of gas adsorbed by unit mass of solid adsorbent and pressure at a particular temperature. The relationship can be expressed by the equation x upon m is equal to k into p raised to the power 1 upon n and n is greater than 1, where x is the mass of the gas adsorbed on mass m of the adsorbent at pressure p. K and n are constants which depend upon the nature of the adsorbent and the gas at a particular temperature. The relationship is generally represented in the form of a curve. In this, the mass of the gas adsorbed per gram of the adsorbent is plotted against pressure. As you see in the figure, at a fixed pressure, there is a decrease in physical adsorption with increase in temperature. These curves always seem to approach saturation at high pressure. Taking the logarithm of equation 1, we get log x upon m is equal to log k plus 1 upon n log p. The validity of Freundlich isotherm can be verified by plotting log x upon m on y axis and log p on x axis. As you can see from the figure, if it comes to be a straight line, the Freundlich isotherm is valid, otherwise it is not. The slope of the straight line gives the value of 1 upon n, and the intercept on the y axis gives the value of log k. Freundlich isotherm explains the behavior of adsorption in an approximate manner. The factor 1 upon n can have values between 0 and 1, and the probable range is 0.1 to 0.5. Thus, equation 2 holds good over a limited range of pressure. When 1 upon n equal to 0, x upon n will become a constant. The adsorption is independent of pressure, but when 1 upon n is equal to 1, x upon m is equal to k into p. That is, the adsorption x upon m varies directly with pressure. Both the conditions are supported by experimental results. The experimental isotherms always seem to approach saturation at high pressure. This cannot be explained by Freundlich isotherm. Thus, it fails at high pressure. Let us now discuss adsorption from solution phase. Solids can adsorb solutes from solutions also. When a solution of acetic acid in water is shaken with charcoal, a part of the acid is adsorbed by the charcoal and the concentration of the acid decreases in the solution. Similarly, the litmus solution, if shaken with charcoal, becomes colorless. The precipitate of magnesium hydroxide attains blue color when precipitated in presence of magnesium reagent. The color is due to the adsorption of magnesium. In the case of adsorption from solution phase, we observe the following. Number 1, the extent of adsorption decreases with increase in temperature. Number 2, the extent of adsorption increases with increase of surface area of the adsorbent. Number 3, the extent of adsorption depends upon the concentration of the solute in solution. Number 4, the extent of adsorption depends upon the solution of adsorbent and the adsorbate. The precise mechanism is not known. Freundlich's equation approximately describes the behavior of adsorption from solutions with a difference that instead of pressure, concentration of the solution is taken into account. That is, x upon m is equal to k into c raised to the power 1 upon n, where c is the equilibrium concentration. That is when the adsorption is complete. On taking the logarithm of equation 3, we have log x upon m is equal to log k plus 1 upon n log c. By plotting log x upon m against log c, a straight line is obtained, which shows the validity of Freundlich isotherm. This can be tested experimentally also by taking the solutions of different concentrations of acetic acid. Equal volumes of solutions are added to equal amounts of charcoal in different flasks. The final concentration is determined in each flask after adsorption. The difference in the initial and final concentrations give the value of x. Using the above equation, the validity of Freundlich isotherm can be established. But there is one drawback of this isotherm. It is that it fails that at high pressure of the adsorbate gas. Langmuir proposed an adsorption isotherm based on the kinetic theory of gases. This is known as Langmuir adsorption isotherm, which could satisfy both at low and high pressures of adsorbate gas. He made the assumptions as you are going to see now. Number 1, the adsorbate gas behaves like an ideal gas. Number 2, the adsorption process consists of both adsorption and desorption. Adsorption is the condensation of adsorbate gas on the adsorbent, and desorption is the evaporation of adsorbate gas from the adsorption. An equilibrium is reached between adsorption and desorption at a constant pressure of adsorbate gas. Number 3, an adsorbate gas molecule is independent to get attached to any adsorption site available to the adsorbent surface. This means the adsorption site on the adsorbent surface is equivalent. Number 4, the rate of adsorption depends upon the freely available adsorption site on the adsorbent surface. Initially, the rate will be very high since more free site will be available. The rate will decrease when more and more adsorption site get occupied, the adsorbate. However, for desorption, the rate will depend upon the occupied site. Hence, the desorption rate will be less initially and will gradually increase as more and more adsorption site on the adsorbent surface gets occupied. Number 5, each adsorption site on the adsorbent surface is occupied by one adsorbate gas molecule. A unimolecular, that is monomolecular layer will be formed once the entire adsorption site on the adsorbent surface is occupied by the adsorbate gas molecules, and no more adsorption will occur. Number 6, the rate of adsorption depends upon the pressure of the adsorbate gas. According to kinetic theory of gases, higher the pressure, higher will be the number of adsorbate gas molecules striking the adsorption site on adsorbent surface. Number 7, Langmuir adsorption isotherm is also applicable for chemisorption. Now, let us discuss the applications of adsorption. The phenomenon of adsorption finds a number of applications. We shall now discuss the important ones. Number 1, production of high vacuum. The remaining traces of air can be adsorbed by charcoal from a vessel evacuated by a vacuum pump to give a very high vacuum. Number 2, gas mask. Gas mask is a device which consists of activated charcoal or mixture of adsorbents. It is usually used by miners and sanitation workers to adsorb poisonous gases such as methane and carbon monoxide. Number 3, control of humidity. Silica and aluminum gels are used as adsorbents for removing moisture and controlling the humidity. Number 4, removal of coloring matter from solutions. Animal charcoal removes color of solutions by adsorbing colored impurities. For example, crude sugar is decolorized by adsorption of coloring matter by charcoal. Number 5, heterogeneous catalysis. Adsorption of reactants on the solid surface of the catalyst increase the rate of reaction. There are many gaseous reactions of industrial importance involving solid catalyst. Manufacture of ammonia using iron as a catalyst, manufacture of sulfuric acid by contact process, and use of finely divided nickel in the hydrogenation of oils are excellent examples of heterogeneous catalysis. Number 6, separation of inert gases. Due to the difference in degree of adsorption of gases by charcoal, a mixture of noble gases can be separated by adsorption on coconut charcoal at different temperatures. Number 7, in curing diseases, a number of drugs are used to kill germs by getting adsorbed on them. Number 8, froth flotation process. A low grade sulphide ore is concentrated by separating it from silica and other earthy matter by this method using pine oil and frothing agent. Number 9, adsorption indicators. Surfaces of certain precipitates such as silver halides have the property of adsorbing some dyes like eosin and fluorescein, thereby producing a characteristic color at the end point. Number 10, chromatographic analysis. Chromatographic analysis is based on the phenomenon of adsorption, which finds a number of applications in analytical and industrial fields such as separation and purification of mixture of substances. Number 11. Ion exchange resins. These resins work on adsorption principle and are used for softening of hot water. I now sum up the entire module point-wise for your benefit. Adsorption is the phenomenon of attracting and retaining the molecules of the substance on the surface of a solid, resulting into a higher concentration on the surface than in the bulk. The substance adsorbed is known as adsorbate, and the substance on which adsorption takes place is called adsorbent. In physisorption, substrate is held to the adsorbent by weak van der Waals forces, and in chemisorption, adsorbate is held to the adsorbent by strong chemical bond. Almost all solids adsorb gases. The extent of adsorption of a gas on the solid depends upon the nature of the gas, nature of the solid, surface area of the solid, pressure of the gas and the temperature of the gas. Relationship between the extent of absorption x upon m and pressure of the gas at constant temperature is known as adsorption isotherm. There are two types of isotherms, Freundlich and Langmuir. Thank you.